Good morning, everyone. My name is Peng Yang from Tsinghua University. It's my honor to be here to present our work on the spectral analysis of network coupling and power system synchronization with varying phases and voltages. So let me begin with the introduction. The center of my topic today is the concept of synchronization. It means all parts of a system operate in unison. It is a fascinating phenomenon observed in multiple disciplines. For example, a group of fireflies will flash on and off simultaneously. Pendulums on a board will eventually swing to the same pace. And synchrony among neurons in human brain is observed in related to the Alzheimer's disease. And in power grids, all synchronous generators should rotate at the same frequency to deliver electrical power. So to study this widely observed and a fascinating phenomenon, we need proper mathematical models. There are basically two types. First is the phase-only model, which only considers the dynamics of phases and assume constant amplitudes. So we can imagine a group of balls rotate at a fixed rate, and this is the phase-only model. But if we relax this assumption and allows varying amplitudes, that is, each ball moves with an angular speed as well as a radial speed, then we get the phase amplitude model. The phase and the amplitude are both described by dynamical equations. Relatively speaking, the phase-only model is mathematically convenient, but at the cost of its explanatory power. So when we put the amplitude dynamics back, we will obtain richer dynamics patterns, but it also complicates the problem. And in power grids, we always say that synchronization is the basis for any AC power grid. It requires all generators rotate at the same frequency. For example, in the pan-European power grid, more than 600 generators should rotate synchronously to deliver electrical power. And loss of synchrony can cause catastrophic blackouts. So to study this important problem, most previous works assumes constant voltages and modeled power grids as phase-only oscillators. However, in real power grids, voltages are actually varying, so we get our amplitude dynamics. And it has been numerically observed that the phase voltage dynamical interplay could indeed desynchronize the system. So far, one essential unanswered question is how power grids synchronize as phase amplitude oscillators. But this is a very huge problem. In this paper, we aim to make a first step to answer it. Generally speaking, there are two parts affect synchronization in a system: force dynamics and the network coupling. The force dynamics are described by dynamical equations of each oscillator, and they are coupled together by the network, which in our case is the power flow equation. So the power grid is a set of network coupled force dynamics. And we are interested in the stability of the strongly synchronized solution. That is, all the time derivative of phases are identical to omega s, and the time derivative of voltages are identical to 0. In this paper, we focus on the network coupling part and try to study how it affects the stability of strongly synchronized solution. So I hope that's enough motivation and background. Next, I will present our main results to that question. I will first briefly introduce our basic idea. Since in this paper, we focus on the network part, previous results have shown that the impact of the network coupling on stability is captured by the network coupling matrix T, which we will specify later. And the spectrum of T indicates the impact qualitatively. That is, if the minimum eigenvalue of T, denoted by lambda mean of T, is greater or equal to 0, then we can say the network coupling stabilizes strong synchronization. Otherwise, it will destabilize strong synchronization. So in this paper, we aim to answer two essential questions. First, we want to know under what conditions we will have lambda mean of T be greater or equal to 0. Question number two, we want to study what decides the value of lambda mean of T. So what is the network coupling matrix? It is given by the Jacobian of the network power flow interaction with respect to the state variables, that is the phases and the voltages. And we denote, we use T to denote its matrix. It is real, symmetric, and can be blocked into 4 blocks, A, D, and C. So we find T itself is complicated to study directly, although its submatrices A, D, and C are highly structured. So here, our basic idea is to study its submatrices first, then use the information of A, C, and D, finally leads to our target matrix T. So let me first present our findings on the submatrices. I will skip the details, but focus on important insights. The leading principal matrix A represents the interaction among phases. It is exactly the network coupling matrix if we consider the phase-only model. So let E be the infinite matrix of the graph. We can reformulate A in this form. So by this, we can say A is actually a weighted graph Laplace matrix. Based on this, it's easy to prove that A is semi-positive definite with a special null space given by span of 1 or 1 vector. So this actually tells us that for the phase-only model, the network coupling always tends to stabilize the synchronized solution because we have lambda of A be greater or equal to 0. So for the trailing principal matrix C, it represents the interaction among voltages. We find the network shunts affect the spectrum of C. By shunts, we mean that a capacitor or inductor connected to the ground in the power grids. More specifically, we find for inductive shunts, for BI0 being negative, it will facilitate C being positive definite. On the other hand, capacitive shunts do not. And we find for typical power grids, we usually have C being at least semi-positive definite. The asymmetric of diagonal block D represents the phase voltage interplay. It can be reformulated again by the instance matrix as this, and it shares the same new vector with A. So the question here is, if we're given stable phase interaction and amplitude interaction respectively, that is, if we know A and C is being at least semi-positive definite, can we say the same of T after they are coupled by this matrix D? So to answer that, we now need a bridge to connect the information of the submatrices A, C, and D to our target. Conventionally, this bridge is provided by the Schur complement identity. It says that for Hermitian matrix blocked in this, if A is non-singular, and then we can introduce the matrix Y here, then we have this identity. So H is positive definite if and only if its submatrix A and its complement are both positive definite. But unfortunately, in our case, our submatrix A is always singular. It has a null space. And C can be singular too. So the Schur identity cannot be directly used. Fortunately, we find the convention Schur identity can be extended in the sense of more Penrose pseudo-inverse. Our lemma 3 says if A is singular with this special null space, and the off-diagonal matrix D shares the null vector, then in the sense of more Penrose pseudo-inverse of A, we can also introduce the matrix Y in this case, and we have the similar identity. So remember our submatrix A and D previously exactly satisfies the null space condition. A has this null space and D share the same null vector. So lemma 3 here provides the bridge we need. Equipped with this, Now we're ready to answer the previous two questions. Our question 1 says, under what condition we have lambda min of t being greater or equal to 0? We find a necessary and sufficient condition. It is given by the matrix inequality which encodes the interplay between phase and voltages. The voltage matrix C minus their interplay should be greater than 0. So if this holds, we can conclude that our target matrix T is at least semi-positive definite. So this is verified by numerical results. This result follows by a key insight that phase amplitude interplay is a natural coupling can handle synchronization. In the phase-only model, you will recall, we always have the network coupling matrix always have lambda min of A being 0. So the network always tends to stabilize synchronization. However, in the phase amplitude model, we may have lambda min of T being negative, and hence the network may destabilize synchronization. This is illustrated by a simple simulation. In the phase-only model, the system synchronized, but after we put voltage dynamics back, the voltage is no longer constant, they have dynamics. Then for the system under the same parameter, we will have lambda min of T being negative, and it is actually too negative to the system desynchronize. This leads to an important conclusion that the widely used phase-only model may lead to wrong results for power grid synchronization. Especially, it is invalid under intensely phase amplitude interplay. So we have lambda min of T being too negative. So for question number 2, we have two propositions as our answers. We find first, lambda min of T is affected by the network shorts, and it linearly depends on the network spectrum symmetric speed. Each of these leads to an interesting insight. The first is we should be careful about adding capacitive shunts, because in power system convention, engineers usually add capacitive shunts to enhance static voltage stability. Our results shows that this has opposite effect from the dynamical perspective. For example, the system can synchronize at the beginning, but after adding capacitive shunts, lambda min of T further decrease and leads to desynchronization. The last insight is that we also should be careful about strengthening network edge weights. It is a common belief in the community of complex network that enhancing the network edge weight can facilitate synchronization. This is true in the phase-only model, but not always hold after we put voltage dynamics back, since when we have negative lambda min of T, increase B will further decrease it. While in the phase-only model, the minimum of the network coupling matrix is always given by 0, so increase this will increase the positive part, it will enhance the synchronization. But it's not true after we put voltage dynamics back. This again tells us how strange things would happen after we put voltage dynamics back and see the power grid from the phase amplitude perspective. Lastly, let me conclude our work. In this paper, we made an initial step to understand how power grids synchronize as phase amplitude oscillators by studying the spectrum of the network coupling matrix. Our most significant finding is that putting voltage dynamics back leads to qualitative change of the network coupling. We find that phase-only model can lead to wrong results, especially when the coupling between voltage and phase are strong. This should be warned. And we also find two interesting insights. For engineers in power system, simply adding capacitive shunts could hinder synchronization. And for theorists in complex networks, we find that this is counterintuitively that simply enhancing network weights may handle synchronization too. So we should be careful about the two-side effect of adding competitive chance and enhancing network weights. And despite the specific power grid background, our results have possible implications in other fields where similar phase amplitude coupling exists. For example, we foresee our methodology can be used in the neural networks and the chemical biology oscillator networks, etc., where the amplitude and the phase couple together. So that's all. Thanks for your attention.
Okay, thank you. Question?
Yes, I'll be very happy to. Very nice presentation. That was very well done. I have, I guess, two questions. One is, can you say a little bit more about your insight, which I found to be quite interesting, where you talked about shunts, and shunts has the effect of basically reducing lambda min T. Can you explain why? I mean, so the way I think of shunts is just basically to add capacitance, and so that increases the lead. So can you explain why this happens?
Yes, sure. Thanks for your question. This insight follows from our proposition 6. It says that it gives the upper bound of the lambda mean of T. Here is lambda 1, but it's the same meaning. It says that it actually follows from that the property of matrix C in the tree spec. Here, we find that the matrix C is highly related to the shunts because it's given by the diagonal is given by BII and off diagonal is BIJ. So BII is actually the summation of BIJ and the shunts BI0. So if the BI0 is negative, it means negative means inductive shunts. It makes this diagonal more positive. So the eigenvalue of C will move to the positive side. But on the other hand, if we add competitive shunts, that is, we add a BI0 being positive, we will move the eigenvalue of C to the left side, to the negative part. So in that case, for our matrix T, since the eigenvalue of T is bounded by lambda 1 of C, the minimum value of C also will move to the negative part. So our numerical result shows that after we add a capacitive shunt, first is -1, then it's 0, add 1 capacitive shunt here, the lambda mean of T decrease. I hope that's clear.
Yeah, thank you. That was clear. The second question I had was, if you don't mind, could you go to your final conclusion slide?
Sure.
Yes. Okay. So can you again provide some insight on what it means to put voltage dynamics back? So now in the grid, we're talking a lot about increasing the DERs everywhere, right? Distributed energy resources. So does that lead to, I'm just trying to understand what putting voltage dynamics back means. Can you give me a qualitative interpretation? When do I need to put the voltage dynamics back?
Okay, so you mean when and why we should put this back?
Yeah.
Okay, we have one motivation is from the inverter interface resources, like you mentioned, DER and so on. Because traditionally, when we study, like in power system, we have the category angular stability. We only consider the phase variables. But in that sense, the assumption of constant voltage is based on the time scale separation. We assume the voltage dynamics is very fast, so we can neglect it, assume it's stable and constant. Second is based on our belief that we can regulate the voltage dynamics and the filter dynamics separately. However, as the integration of DERs and inverter devices, we find that it has been shown that the voltage dynamics and the phase dynamics, they are more tightly coupled compared to the traditional synchronous generator. So in that sense, we think it's interesting and important to look back the assumption maybe constant voltage is not valid anymore, so we should put voltage dynamics back.
I see. So does that mean that I have to design the control strategies for all of the smart inverters in a different way?
I'm not sure about that, but I mean, if you can also maintain the voltage dynamics being stable enough, like the past for synchronous generator, if we can make sure the inverters they have stable enough voltage dynamics. So, for example, our condition here, C minus this voltage inequality can be guaranteed to be always hold. So it will be no difference. But if the voltage dynamics is not stable enough, it has to be considered to do some control and etc.
All right, thank you. No further questions.
Okay, one question from me. So there are a lot of published papers on this type of network synchronization problem. So have you looked at conventional work to, the previous by others, I'm sure you know some names, Francesco Bullo, David Here, Guangdong Chen. So what's the connection? You have not cited any of their papers. What's the connection between your work and their work? Because sometimes they can consider nonlinear interconnection, nonlinear coupling as well. Of course, they use different type of arguments. Some people use a matrix-based analysis. Some people use a Lyapunov dissipativity theory. So what's your connection like, So I try to understand,
Yeah, thanks for your question. It's very good question. And the previous works, as I said, most previous works, when they study the power grid synchronization, they tend to use the phase-only model. They will assume constant voltages. I list 3 typical work here. And for David Hill, they also used the phase-only model for most of their work, but recently I read a paper about their phase voltage models. But the key idea, I think, relate our work to their work is, to the best of knowledge, to the best of my knowledge, that we first find that the inclusion of voltage dynamics can make some changes to the network part. And in terms of methodology, I think the methodology is quite standard. We use the matrix analysis here. So does David Hill and others. When they study the stability, I think this is quite standard. And yeah, for nonlinear parts, we also consider the nonlinear power flow equation here. But yes, of course, when we study the stability, it is linearized by Jacobi. So I hope that's clear for your question.
Okay, so you do consider stability, but for linearized model.
Yes, we can say that. We stopped for nonlinear model, but when we focus on the stability, it is linearized.
Okay, fair enough. Thank you.
Thanks.
Okay, just one query. You have concluded that the phase-only model will lead wrong results. But in practice, is there any such examples showing you have wrong results, although they have wrong results in practical such?
Sure. Thanks for your question. It's very important question. Unfortunately, we not have this practical examples yet. It is shown by our simulation and theoretical analysis, but so far we don't find practical importance. But we think it's very important. It will strongly enhance our work.
I agree. I completely agree. I mean, especially because we are going to have more and more DERs. And since your point is that normally we neglect that coupling, and as we increase DRs, that coupling cannot be negligible anymore. And if you can demonstrate that, your results will have a lot more value.
Yes.
It's a very good question.
Thanks. It's very good, very important question.